I have to start with a silly thing, but if you would all smile, that would help a lot. Yeah, that's okay. Yeah, good enough. Right, do we get... Ooh, the colors are a little bit off. Anyway, first of all, I have to say congratulations. You made it mostly through the day already, and it was a pretty long day. There were a couple of interesting talks. In fact, right now there's a colleague of me, James Burney, talking about quantum computers. And if I wouldn't be here, I would definitely go to that talk. But instead, I'm going to talk about the machine learning landscape that we have today. And first, something about myself. I'm Aiko. I work for a company called ThoughtWorks. We do consulting. So we write individual software for different clients, different domains, different technologies. We try to do what we would consider the best practices. We try to be agile, test-driven development, continuous integration, continuous delivery, and pair programming, all these sorts of stuff. And working for a consultancy kind of makes me a consultant, but what I actually am is a developer. And my passion is machine learning. And that passion started when I was at university. I wrote my thesis about convolutional neural networks on mobile devices. And then later, when I joined ThoughtWorks, I worked, like one thing that was kind of cool is I worked at a client in Germany, which is an online retailer. In fact, the second largest, right after Amazon. And what we did there was we used neural networks to predict orders based on browser session data. So we looked at browser session data that was coming in from a user that was visiting the page, and then we tried to predict on previous data how likely it is that that user will buy something. And if it would be unlikely, we would then give some discounts on things. But enough about me. Let's talk about machine learning. And there are a lot of hype terms currently that everyone is using, and I think it would be good to get a general common understanding of what these words mean. And when people talk about artificial intelligence, there's this definition I really like, that is also the definition that Google uses, that artificial intelligence is the theory and development of computer systems able to perform tasks normally requiring human intelligence. So artificial intelligence, AI in general, is nothing special so far. It is just that everything where you would think a human needs intelligence is then done being automatically by a computer. For example, a chess program, which simply can just brute force all the possible solutions, and then you play chess against that. This brute forcing, when we do that, when a human would do that, we would consider that intelligent. You need to be intelligent to play chess. And if a computer is doing that, that's just artificial intelligence. So nothing fancy so far. What I consider fancy is the machine learning part, where we actually, the algorithm that the computer follows to achieve something is actually defined by the data we put into a machine learning model. The algorithm changes with data I put into the model, and I think that's kind of cool. And then there are neural networks. Neural networks are a subset of this machine learning thing, where the model is kind of modeled after the human brain, which has neurons, and then they're all connected. And then there's fancy deep learning. And deep learning is basically just a neural network with many layers. I'll talk a little bit more about that later. And what's also cool nowadays is data science, and data science can use a couple of these approaches. But in general, data science is just getting insightful information out of some data. And you can use these, or you can use other methods. Right. So I said machine learning is my passion. And then earlier this year, I wanted to do something cool with machine learning, and I wanted to use cool machine learning technologies. And then I remembered this quote, and I think that still applies, and I think we do that a lot in our industry, that we always go for the cool kid on the block. Larry Ellison is the founder of IBM and the CEO, and I think that still holds true, and that quote is like 10 years ago. And I have to ask you a question, and I will ask you to raise your hand. How many of you use Apache Kafka at work? Well, that's, so for the people watching, please hold your arm, there's a follow-up question. That's about a third, maybe 40%. And how many of you think Apache Kafka is the perfect solution for the problem you are solving with it? Oh, half the arms go down. So apparently, I mean, Kafka is cool, but I think that kind of proves the point that this is still valid. So I realized earlier this year that I had to do my own analysis rather than just following what's cool. And then I looked at the machine learning landscape, and what I found was that the vast amount of technologies out there it can be quite overwhelming. And then in this talk, I try to lift the fog a little bit around, like what technologies, what tools are out there, and what they are good for. And I'll be focusing on machine learning and a subset, like the deep learning subset, and then I think I have a slide for natural language processing as well at the end. Right, so when we talk about technologies that can be used to analyze data, the only reasonable approach, of course, is do it data-driven. So what I did was I compared all these tools based on popularity, for example, and the popularity I took the GitHub stars for these tools. I looked how easy they are to set up. I looked at I read the API docs. I mean, not completely, but I looked at it. I played around with some tutorials, and when possible, I try to include expert opinions in general to get a better understanding of which technologies are out there and what they are respectively capable of. So that means that I'm not an expert in all of these technologies. I've worked with some of them, definitely not all. So if one of you have worked over the last 2 years with one of the technologies, you probably are more an expert in that particular technology than I am. However, some of the technologies are rather new and came out in the last 2-3 years, and probably no one can be an expert in all of them, so that kind of saves me a little bit. So now that I've done all this analysis, obviously you're asking, hey, you spent all that time, so what's the best tool? And as a classical consultant, I have to answer, it depends. And it depends, in fact, on a couple of things. It depends on the use case, whether you are building image classification for signature checking or for optical character recognition, or you want to do order prediction, like we did at the client, where we used browser session data to predict orders. And in general, if the tool can't solve the problem you're trying to solve, don't pick that tool. That one sounds obvious, but then again, lots of hands went down when I asked whether Kafka is the perfect solution. It also depends on the experience or your team's experience and the experience regarding the language that the tool uses, regarding the tool themselves, and regarding experience with machine learning. It depends on infrastructure, whether you will later run on a powerful server or whether your model will be running on a mobile device, for example. Whether you do the training on unlimited resources in the cloud, or whether you have to train your model on a GPU, on a laptop without GPU support. And it depends on the structuredness of the data, meaning where's your data stored? Is it stored in a graph database? Is it stored in a Hadoop cluster? It depends on the feasibility of a solution, and by that I mean whether you're doing prototyping and research, or whether you are ready for production. that changes a little bit. In general, the question is whether you're trying to find the general correct model to approach your problem, or whether you do production fine-tuning to get the very last bit out of your solution. And obviously, it depends on how much data you have, whether you are analyzing the click stream of Amazon over the last 5 years, or whether you are looking at the cookie recipe collection of your grandmother. Depending on your grandmother, there can be significantly less data. And it depends on a couple of more things, like how much time do you have, the size of your team. Right. And to give you a little bit better insight of how I approached this whole thing, I'll give you some examples. And we can start with the most popular one. Probably most of you have heard of TensorFlow, deep learning framework, open source by Google, with like more than 100,000 stars on GitHub. And what I did is, for all of these technologies I had a look at, I gave them marks on different categories. And so I think the most prominent one here is the ease of setup that only has 2 out of the 5 stars, where 5 would be the highest. And the reason for that is I had a look at the installation page for TensorFlow on Ubuntu. So I went to the web page and it's like, hey, how do I install it on Ubuntu? And this is what I got. That's a lot of stuff. In fact, I had to install a browser plugin that automatically scrolls down, takes a picture, and stitches this together. So there was quite a little bit. To be honest, there are some parts about only GPU and only CPU, and there's a little bit about Docker. But in general, it is a lot of steps you have to follow to install TensorFlow. And then now you're asking yourself, why does it still have 2 out of 5, where 1 would be the worst? So I went to the Microsoft Cognitive Toolkit website and did the same thing. And then this browser plugin told me I can't even comprehend so much, because the installation page was even longer than the one of TensorFlow. So that is for Ubuntu, though, and in Microsoft's defense, apparently installing it on Windows is fairly easy. But who does data science on Windows? Right. But there must be something that TensorFlow does right, otherwise it wouldn't be so popular, right? And one thing that TensorFlow has, it's called TensorBoard, which nicely visualizes in real time the training of your model. You can see some nice graphs, and it even shows the computational graph. I'll explain later what that is a little bit. You can even visualize the computational graph and zoom in, and that's all pretty good when it comes to the ease of use. However, there still are 2 points missing, and the reason for that is that TensorFlow has a very complex API. It has lots of things you can do, and it exposes lots of hyperparameters that you can play with and adjust with later on, which then gives 5 marks for the degrees of freedom you have, or the parameters that are exposed, because you can do the nitty-gritty detail and can go into that level of detail. But it makes it a little bit more difficult to use. And then there's the adoption one, and the adoption one is, in general, you can maybe say they're doing something right if it's fairly popular, but what you can definitely say, if there's a big community around it, that you have a certain level of support. If you run into problems and there are millions of users, the chance that you get an answer on your question is higher than if it's a very small community who maybe don't even care about you. Right, that was TensorFlow. Another tool that I'll be talking about is Keras. And Keras is not actually a deep learning framework. Keras is something different. It's a higher level interface that offers a more intuitive set of instructions. It is a right. It is very easy to build neural networks with it, and in fact, you can define a long short-term memory network in about 10 lines of code, which is pretty cool. So Keras takes care of lots of details that other frameworks where you would have to basically do it yourself. So Keras takes that away from you. It's pretty popular in terms of when it comes to prototyping and building POCs, or you're exploring different solutions. And it works on top of other frameworks. So you have, for example, TensorFlow, and you can put Keras on top. Like you write your network, you write your model in Keras with the easy API, and Keras then translates that into some TensorFlow code and takes away the details from you. And currently supported is MXNet, Deep Learning 4J, TensorFlow, the Microsoft Cognitive Toolkit, and Theano. However, there is a drawback, obviously. If everything is so easy and all the details get abstracted away from you, you lose that fine-grained control. Then there is the ease of setup. Keras is basically pip install. But as I mentioned, you need what they call backend, which is one of the other deep learning frameworks installed already, and then you can use TensorFlow on top. And if you want to do like low-level stuff, like define multi-GPU support and things like this, you can't do that with Keras. You have to do that on the backend framework in that case. Right. So one other thing I did was I separated general machine learning libraries, which are these one, from deep learning libraries. And the reason for that is that the resource requirements for deep learning frameworks or for deep learning are a little bit different. And all the deep learning frameworks that come later that I'll be talking about all have GPU support. And the thing is, deep learning is, as I mentioned earlier, a hype word, and it's cool. If you can solve your problem with a linear model where you don't need deep learning, then please solve it with the more simpler approach, because the deep learning frameworks all have a little bit more complexity when it comes to the setup, and a little bit more complexity when it comes to using them. So if you can solve your problem with an easy approach, go with that, and don't go for deep learning. Right. So considering the technologies that we just saw, I plotted them against each other, where on the x-axis we have the adoption, and on the y-axis the degrees of freedom. And the size of each of this bubble is the ease of use. And we can, what I'm not having displayed here is the ease of setup, because for these, they're mostly pip install, conda install, or brew install, or apt, or some of them are just a jar that you add to your dependencies. So the setup is quite easy, quite simple for all of them. We have a couple of libraries toolkits here, which is Weka, Shogun, and PyBrain. And they are not particularly popular right now. In fact, PyBrain is being discontinued. I don't think there was any change on the repository for the last 2 years. And Weka has a graphical user interface, which also doesn't seem to be that popular in the community. However, Weka seems to be doing quite well when it comes to data mining. On the very right top, you see scikit-learn. Scikit-learn is, some of you might have heard of it, is quite popular and is highly adopted in the community. And it offers a quite powerful model. It offers a lot of algorithms, a lot of machine learning algorithms that you can pick. And you have lots of parameters exposed where you can fine-tune your model. Then we also have, and I kind of grouped them in these community friends and community kings. It's fluent, but there's also H2O and MLlib. And if you're working with Spark, you might be interested in these. So scikit-learn offers a Python interface. H2O and MLlib, in fact, Spark comes with MLlib, and there even is a higher level wrapper on top of MLlib, which is called SparkML. So working with Spark, these are interesting. H2O there are a couple of use cases where H2O is maybe better than MLlib or SparkML, but the good thing is if you work with Spark and work with MLlib anyway, you can add H2O later on without any problems. There is another perspective on the landscape for machine learning libraries is the scalability. And again, we have the degrees of freedom on the y-axis and the ease of use represented by the size. To keep the adoption rate in mind, I colored the bubbles a little bit. Scikit, again, has the most degrees of freedom and the highest adoption rate. However, it is limited to a single machine. And that becomes the problem. There are some algorithms that can be implemented to run multi-threaded, and they run multi-threaded. But the problem comes definitely when it comes to the amount of data, because running on a single machine also means your data needs to fit into memory, unless you do batch jobs, which there are cases where that works, but in general, that doesn't, and then you run, basically, you're limited by the amount of memory you have. Then we have, as I mentioned earlier, Apache Mahout, MLlib, and H2O, and they run on top of Spark, and they can run on an HDFS. The general learning from this is that if you need scalability and you have a certain amount of data, you need to consider, well, that's basically the question. Do you have that? And then you need to consider this in your choice of tools. And later we will see that this is about machine learning. When it comes to deep learning libraries, they are all highly scalable. That's the point of it, basically. All right. Talking about deep learning frameworks, there are a lot of them, and that's what I mentioned earlier. They are also capable of the same linear approaches that the other libraries that we saw before are capable of. However, in certain cases, for certain use cases, deep learning has significantly higher success rates. If you, for example, talk about computer vision, I think all the successful computer vision nowadays is done with deep learning networks. The same goes for speech recognition, audio recognition, and machine translations. These are all fields where deep learning has significant advantages. And there are disadvantages as well. As I mentioned, it's a little bit more complex, so it's harder to set up. In general, you need a little bit more data than with the simple approaches. There is something called transfer learning, where you can train a model with one set of data and then use that model later on and take the trained data with you. However, I've so far only seen that being done for image processing, for image recognition. And if you have structured data like a table, I haven't seen that being done. So for deep learning, you, in general, need a little bit more data. And a thing is that deep learning models are more difficult to comprehend, to understand what the per feature importance was for a certain outcome. You give in some data, and then you get a result. And which data point actually led to the special result that you are getting is significantly more difficult to understand in deep learning. And there's my favorite example is a physician, like a doctor, who types in symptoms, and then the deep learning model predicts, oh, this is this condition. And for a doctor, like, I personally wouldn't want a machine to determine my physical condition. And I would like to see the doctor actually have a look over it and understand what was going on. And if you have a deep learning model, that is significantly more difficult than if you have like a shallow network, or like a non-deep learning model. Right, so how do deep learning frameworks work? A lot of you probably have seen this before, I hope so. I'm not going to get into the detail. This is the architecture of a neural network. You have input nodes where you put data in, and they are, in this case, connected to the next layer. Like all of these nodes are connected. All of these nodes in the first hidden layer has a connection to the first one, and they are connected to the next hidden layer. And then there's an output layer. And all of these nodes do some calculation. The easiest way, or the easiest case, would be just to sum up all the data that I get, and then if I reach a certain threshold, I give in a certain value to the next layer. And so this is a fairly small neural network. I'm not sure what it actually would be capable of doing. When we talk about deep learning, the amount of layers would be significantly higher. Not 2, maybe 50, 100, significantly more. And also, in general, the number of nodes per layer are higher than displayed here. And how do now deep learning frameworks work with this kind of architecture? Typically, deep learning frameworks create something that is called a computational graph, which is a directed acyclic graph, so a DAG. And what it's doing is basically figuring out which calculations needs to be done before the next calculation can be done. So in order to calculate whatever this node is calculating, obviously I need the previous layer nodes to have calculated their calculation. And that's what this layer does, and then it pushes forward the calculational results. And the deep learning frameworks offer a couple of things. So they offer the general building blocks, like you see these nodes and layers. You get that. You get other kinds of machine learning algorithms. They're all highly optimized. So as you can usually write your network in Python, and then since Python isn't really that fast, the actual calculations would be done in C++, closer to the machine. And that is, for deep learning, fairly important because the computational requirements are quite high. And as I said, they all support GPUs, and that can reduce the training times from days and weeks down to hours. And this is the landscape of the deep learning frameworks where the adoption is plotted against, again, the degrees of freedom, and the ease of setup is indicated by the color, and the size shows the ease of use. We've talked about TensorFlow and Keras before. These are what I would call the community kings. They're quite popular, and especially in combination with each other. So Keras on top of TensorFlow gives you this nice, easy to comprehend API, but the powerful implementation of TensorFlow in the backend. And even then, you can do the fine-tuning of your model in TensorFlow directly. And then in the middle is what I call the community friends. So the thing is, so all these companies who have a lot of data, be it Google, Facebook, Microsoft, and some of the others, having data is one thing, but you need some way to understand it, right? You need some way to analyze this data. And that's one of the reasons why they have all open sourced their deep learning frameworks, so that the open source community can have a look at it, fix some bugs, test a little bit, maybe request some features, maybe build some features. And in order for these companies to have the maximum amount of analytical power for them, they that's where I see them all fighting a little bit for attention. And in this case, they're fighting against TensorFlow and Keras a little bit to get that attention of the open source community. Then there is, on the top you have Theano. Theano is a quite old, one of the first deep learning frameworks. It was developed by the University of Montreal. However, the University of Montreal, or the team that was building Theano, decided, due to the large landscape, due to all the other deep learning frameworks, that it's not necessary anymore to have Theano. And I can see Theano being deprecated quite soon. The support stopped at least this year. And then there's Caffe 2. Caffe 2 is developed by Facebook, and it's getting more and more popular, and I can see that moving into the direction of the community friends in the middle, which are fighting for attention. Caffe 2 also has the repository on GitHub has been merged with the PyTorch repository. I'll talk about that a little bit later. In general, Caffe 2 is a rewrite of the Caffe framework, which is also quite old compared to the other ones. But Caffe is still being used, especially when it comes to computer vision. However, it has a C++ interface, which is not unique anymore. Some of the others also support C++. And Caffe uses architecture definition in YAML, which might not be to the likings of everyone. And then there's this tiny bubble is Torch. Torch is also fairly old. It has a small community. It's written in Lua, and Lua is also the language that you use to interact with Torch. And then on the very left, there's Deep Learning for J, which, as the name suggests, is Deep Learning for Java. And similar to Caffe, the fact that it is written for Java and they can use Java is not unique anymore, since a lot of the other ones also have Java interfaces. In general, TensorFlow is particularly good when it comes to distributed infrastructure. They have a couple of tools that makes it highly efficient to run on distributed infrastructure, and they have some algorithms to deploy calculation on different nodes fairly effectively. However, pure TensorFlow without Keras has a quite comprehensive API, and that leads to a steep learning curve. There's one more thing to consider when you need to build a solution based on deep learning. Because the path to success in general in machine learning is not always obvious. What you usually do is you play around with certain hyperparameters, you try out different architectures, you often explore multiple options before you know which is the way to go, which offers the best solution for your problem. And that means the ability of a framework to actually make that fast prototyping, to have to be able to build POCs, to research what is the best approach, that can be a deciding factor for or against a framework. On the other hand, when it comes to the closer you go to production, the more fine-tuning you want. And these kind of contradict each other. But that also leads to the fact that in different phases of the development cycle of your product, of your project, different frameworks would be recommendable. And now there's MXNet, which has these nice arrows, the arrows indicate that MXNet has two different kinds of APIs. One is a fairly low-level API, and on top of that, there's a more higher-level API. So you can work with the same framework initially to do some fast prototyping, figure out which is the right approach, and then later switch to the more detailed one, and then when it comes to production. But does that now mean that for all the others, you have to write some, like 4 weeks, you try something on the left side of this, and then you use that framework for 4 or 5 weeks, and after 5 weeks you have to throw away your code and try everything again with another framework, and then 5 weeks later you have to write the same thing again with a different framework? Well, I think that would be a horrible idea, and other people agree with me, and there are solutions. And there's framework interoperability solutions that are currently being developed. Onyx, the Open Neural Network Exchange is one of these solutions. There are other ones. And this is basically a defined format of the model that is being used by Caffe2, by the Microsoft Cognitive Toolkit, by MXNet, and by PyTorch. And that means you can write in the beginning of your product, you can write in this one framework, and then later when it comes to production, you can just deploy it onto some other framework, and it just works like this. And even though TensorFlow isn't storing the model in this specific format, there are also converters who then convert the TensorFlow format to Onyx, and the other way around. In fact, we have, with Facebook, as I mentioned earlier, is the one developing Caffe2. Facebook is also developing PyTorch, and what they do at Facebook is, in fact, they use PyTorch for fast prototyping, for finding the best general approach and building the model, and then later deploy it to production using Caffe2. Right. Another thing is the question whether you are solving a core problem of your domain, or whether you are just solving a peripheral problem. When it comes to the core problem, you want as much control over the model as possible, right? And it's okay if you put a little bit more effort into it. When it comes to a peripheral, which is not really your use case, but you would like to get it done somehow, then you want a little bit more convenience. And an example here would be, let's imagine you work for a dating site, and they have this register page, and every user has to send in a photo of an ID, like a driver's license or a passport or whatever. And people at your company have to manually verify, that's the correct person that signed up. But the problem is, most of the people don't want to send in their ID, so they just upload anything, just some picture, and hope that they just get through that. And then you realize all these people at your company doing the manual checking, now you waste a lot of resources because they're not actually looking at IDs. And having a simple tool that would just figure out, hey, the photo uploaded, is that actually an ID or not, is definitely not your core domain, because your core domain is bringing people together, like you're dating, and have cool algorithms to find how they match and whatnot. But this sign-up page is not your core, it's peripheral, but it would be nice to save some money. And in that case, having a simple solution that doesn't need a lot of effort, but maybe gets rid of 50% of these fake IDs that are being uploaded, would already help a lot. On the other hand, a different example, imagine you're working for an online retailer, and you want to do product recommendations. The correct product recommendation can have a significant impact on your business. It's about selling stuff, right? It's about the money. The better your product recommendation is, every percent your product recommendation is better, the more money you make. And in that case, you want to have a lot of control and you want to put a lot of effort into fine-tuning to get like 0.1% better predictions of your model. There are a couple of, I step aside here, the ones on the very left of the screen. And they're not actually Google Cloud, and they're not AWS, and they're not Microsoft Azure. Those are placeholders for different specialized as-a-service solutions that these cloud providers offer. And they are fairly specialized. They range from optical capture, character recognition, to landmark detection and face detection and text-to-speech translation and speaker recognition. The thing is, they are super convenient, right? If you need to do landmark detection, you can just upload your image and it tells you what landmark it is. But you can't train the model, so you can't actually change the prediction. You basically upload something, some data, and you get a JSON back telling whatever that model predicted. If that works, if that solves your problem, and you are fine with paying some money for it, and you're fine with sending your data to one of those cloud providers, go ahead. That would be probably the best solution you can find. However, if you need more control, then you probably have to build something yourself. Another way to look at it, and I'm using some NLP tools here, is whether you need domain knowledge, much domain knowledge or less domain knowledge. And it is a little bit similar to the peripheral core comparison. And these tools, they don't actually all do the same, but it still works for this example. If you, for example, want to automate chat ops, so chat ops is basically you want to deploy something to production, you just go to Slack and type deploy artifact 1, 2, 3 to production, and then everything happens, right? The ChatOps solutions that I've seen so far are more or less all some kind of command line interface. There's no fancy language processing, it doesn't understand you. You literally have to type exactly what it's supposed to do, and then it works. And in that case, you don't need much knowledge about the domain. You basically just take whatever is written in that chat window and then run it on a machine. However, if you, for example, want to do topic modeling, which is you look at a certain body of text and then find out what the text is about, you need some kind of understanding of the domain. You need some kind of knowledge of what certain words mean to figure out, okay, this text is about this topic and this text is about the other topic. And if you, for example, go to write a news summarizer, which is basically you have a long article and you like shrink it down and you pick the most important things out of it, the most important sentences and the most important information, maybe cut a couple of sentences together. In that case, you need even more. You need a little bit even more domain knowledge to understand what's going on, which are the important sentences, which are the less important sentences, which ones can I combine together in a way that it still makes sense. And continuing on the more domain knowledge side, a medical diagnosis bot. So you type in your chat window and your chatbot your symptoms, and you want the chatbot to then tell you what condition you have. Let's put it this way: you don't want to get that wrong. If someone gets serious damage, or like you predict something horribly wrong, and then that person has a medical condition that you didn't actually predict, or the opposite, you prescribe some kind of a medicine that is more dangerous than helpful in that situation, that can be quite devastating. So you want to have a lot of domain knowledge in that situation to really understand what these symptoms actually mean. And I think the worst part the most difficult one of the most difficult NLP problems is understanding legal documents. So when you think about terms and conditions or even some other contracts, let's face it, not even humans can understand what's written in there. Some lawyers can, but normal humans not really. And then for a natural language processing system to understand all of that, that is, you need to have the complete understanding of the domain to not make any mistakes. On the very right, a Dialogflow, which was previously known as API.ai, and Wit.ai and Rasa, they offer conversational interfaces. You can't really build anything. You don't really need to build anything yourself. You just have this conversational interface where Wit.ai and Dialogflow are basically online HTTP APIs. You can't train the model. You just like send some text and you get some analysis back. Rasa NLU runs locally and similar to the has a similar API. And admittedly, the conversational interfaces as a service have become quite powerful. I mean, we all kind of know how Google works and Alexa. And my phone reacted when I said, "Okay, Google." Right, but they only work if you don't need specific domain knowledge. You can't say, "Hey Alexa, I have these symptoms. What medicine should I take?" This domain knowledge is not. Alexa doesn't know that yet, but maybe at some point. Right. That was my analysis of the machine learning landscape. I hope I could give you some ideas on how to pick the right tool, which question you want to ask, which question you have to ask to make a right decision on the tool. And you can follow me on Medium and on Twitter, but I don't really post anything on Twitter unless I write something on Medium. So just follow me there if you want to. Other than that, thank you very much. We have some time for questions. Well, let's maybe take the mic. Yeah.
I just want to try this machine learning, deep learning, and so on. What framework will you advise?
So there is Keras that makes it fairly easy. Maybe there is something else which
there was also Veka, but it was not present on the last slides.
There's something really cool. There's something called fast.ai. And I learned about that. I'm currently working in Bangalore, and they have these weekly meetups. And basically what they do is every week they do this workshop session. And they have the fast.ai, this framework is on a very high level of abstraction. You can start with it without actually knowing any deep learning or machine learning for that matter. And step by step, you can literally you can do model.fit, and then it does everything, right? So that's pretty crazy. And then you can do. There's lots of text you can find here written on this side. And you can then later, even though it has this very high level of abstraction, you can also go a little bit more into detail. And this is exactly what they do in these weekly meetups, where you start on a high level. I think the first thing is cats and dogs, and then you train your model, and then you put in a picture of a dog, and it tells you it's a dog, and you put in a picture of a cat, and it tells you it's a cat. It has this very practical approach where you where you do the practical thing, you get a nice result first, and then later you go more into details and learn about the theoretical background of machine learning.
More like application question. If you do have experience or you're investigated that integration between those frameworks that you've reviewed and shown in this presentation, many thanks for presentation itself, very nice. In terms of cloud providers, mainly AWS or Google Cloud, like if you would say, like if you want to reduce the pain in several places when you're trying to combine your like classical transactional processing system based on, let's say, AWS, and you want to build some analytical solution integrating with one of those frameworks, what practical surprises, let's say, do you have, or something if you can recommend?
Well, that's a pretty good question. Maybe I'll repeat the question to make sure that I understood it correctly. It is about framework interoperability, basically when you're running on one of the cloud providers. Okay. Haven't done that. So in general, all these cloud providers have some kind of, apart from the special solution as a service, these as a service solutions for landmark recognition. They also have some kind of preferred deep learning framework. Obviously, when we talk about Google, you can get your TensorFlow instance like this, right? Because Google is the one behind TensorFlow. And when you go to Azure, they have their Microsoft Cognitive Toolkit, which you can get like this. I'm not actually sure how it works when you go outside of these boundaries. In general, you probably have a little bit more effort when it comes to the setup, the general setup, because you have to do more things yourself. But I don't think I wouldn't expect particularly more difficulties than the normal setup. The migration, and especially if we're talking about like Onyx, this one format, it's a file, right? So one framework does one file, and if you have a different framework somewhere else, just shove the file over, and then you can do the same thing. So I wouldn't expect that many complications, rather than set up a non-proprietary system on that cloud provider system.
Thank you.
My question is the following. I tried to start learning machine learning, tried different algorithms, but a problem which I met is to find data sets. Maybe you can advise something, how to search?
There is Kaggle.com, I believe, which is a fairly large database of different data sets, and they have some kind of competitions. So you, I'm not going to click through it, but there are some competitions where it basically says, hey, this is the data set, and this is what we want to find out, and then you can do whatever you want with the data set, and then just upload your result, and then some people are, I mean, you can even, some of them competitions actually have money on it, and then there are some companies like saying, hey, this is the data we have, and even apart from the competitions, there's a large amount of data sets available for different purposes, images, text, whatever.
Thanks.
I have more TensorFlow question. So it provides multi-language clients. So does Python better than Java or something like that? Or you can do like whatever you want?
Right. Let's say native interface of Python of TensorFlow would be Python, and there are certain ways how to get the other languages. There's this WSIG. Anyway, so not all of them offer the full feature set. In fact, there is also the C++ one, which most of the underlying stuff is being written in anyway. I use the C++ one. I'm not a big fan of C++. I think I did too much of that. But I think it depends from language to language which features are supported and which not. By now, I would think that Java is, given the popularity of Java, and TensorFlow is about 3 years old now, and I think you can do most of the stuff, but I would probably try to read it up yourself before making a decision based on that. All right, no more questions. Time for Pivo.